Now let's look at an example contract that I put into this module, oracle.swap. And the idea is that it's a smart contract where somebody can put ADA and then somebody else can exchange those ADA for a token. So in our example, we will use some token that we call USDT for US dollar token. The idea is the price, so the amount of USDT tokens that the buyer has to pay for the offered ADA will be determined by the Oracle value. So that will change over time depending on the exchange rate encoded in the Oracle. And so the idea is that we use Loveless and we also use this US dollar token with a factor of 1 million. So $1 would correspond to 1 million of those tokens. So I start with a helper function that I call price, given amount of Loveless and an exchange rate, expressed, as I said before, as an integer that where the actual rational number is multiplied by 1 million, get the price of that token. And I must just multiply the Loveless by the exchange rate and divide by 1 million. Second, just another helper function, given a value, extract the amount of Loveless in there. They're called Lovelaces, and that's just a combination of two functions provided by the Plutus libraries. First, given a value, I can get ADA, and then given the ADA value, I can get the number of Lovelaces. And then I can provide this swap validator. The idea is that it takes two parameters. It's a contract with two parameters. The oracle we are using, that comes from this other module that we discussed before, which I'm importing here. And I'm importing another module that I call funds. We can look at that in a moment. And second parameter, the address. This will be the address of the oracle. So normally, given the oracle, I can compute the address from it. In the core module, we saw a function oracle address that takes the oracle and computes the script address from it. But that is a function that I can't use in a validator because it uses code that is not compatible, that can't be compiled to Plutus script. So I'll use a trick here and explicitly hand in the address as well. So when I actually call this validator later, I will compute the address from the oracle. But now I just give it as a second parameter explicitly. And for datum, we will use the pub key hash, which is the pub key hash of the seller that will receive the price. And we don't use an interesting redeemer, so we can just use unit. Okay, and if you recall from the diagram, so such a swap transaction should have three inputs, so two script inputs, the oracle to check the current exchange rate and the swap output that holds the Loveless, and then as a third input where the funds are actually coming from the buyer. And it should have three outputs, the oracle output again, but we don't have to worry about that because the oracle validator takes care of that. That we saw in the core module, that the oracle validator makes sure that whenever it is used, there will be an output with unchanged datum and added fees, if you recall. So we want that, and then the seller must get the tokens, and the buyer should get the locked Loveless. And we want to support a second use case, namely that the seller can retrieve his assets. Otherwise, they could be potentially locked there forever. So there are basically two ways to unlock the Loveless locked by the script address. One is if somebody actually does the swap, gives tokens to the seller in exchange for Loveless. And the other is that the seller himself retrieves the Loveless. So doesn't want to do the swap anymore and gets his money back. So this is the first condition. So if the seller himself signs the transaction, then it's fine. There's no additional condition. There doesn't have to be an oracle involved or anything. So if it's signed by the seller, he can just get his hands back on the Loveless. And the more interesting case is the second one, where we check two conditions. First, we check that there are exactly two script inputs, because we only want the oracle and we want this swap UTXO itself. All additional inputs to pay transaction fees and to actually pay the price must be public key inputs, because we don't want to worry about interference with others' smart contracts. And secondly, we want to check that the seller gets paid. So we define a couple of helper functions to check this. So again, we define the info extracted from the context. Then we find the oracle input, and we do that by taking all the inputs that we get from the info field. So this is a list of all inputs, and I'm using list comprehension here. So that's a nice way to construct lists in Haskell. So it has this syntax with the square brackets and then vertical bar, and I can basically draw from other lists. So this says I is now basically looping over all inputs of the transaction. Then I can have let expressions in such a list comprehension as well. So I is an input, and I compute the corresponding output with txin info resolved that we saw before. And I can also put filters or conditions here. So if the condition is satisfied, then this I will be kept, and otherwise it will be dropped. So and the condition I check here is that the address where this output sits at is actually this address parameter, which, as I said before, will be the oracle address. So this tells me get all inputs with corresponding output O that sit at the oracle address, and I keep all those O's. And then I check that there's exactly one of those. So I make sure that there's exactly one oracle input. Otherwise, I throw an exception. So this now gives me the oracle input or output. The oracle input consumes the oracle output. Now I want to check the actual exchange rate. And I use this helper function that we defined in the core module that given the output where the oracle sits, computes me the actual exchange rate, the datum, the integer datum. And as before, so I apply that to this oracle input that I found in the previous helper function, and again use find datum info to look up the datum to a hash. And this can fail, in which case I didn't find an oracle input, or it can succeed, in which case I provide the X. And I was just wondering whether I forgot to check that this oracle input actually holds the NFT, but I don't need to check that because seeing as there is an oracle input, we made sure of this here. We know that because of how validation works, the validation script for the oracle input will also be run. And if you recall from the core module, that script checks that the NFT is present. So we don't have to do that here in the validator for the swap. Okay, and now this check here has two script inputs. So we loop over all inputs and we filter with this function. So this gives us the output to the input. This gives us the address of that output. This gives us the hash, validator hash of this output if it's a script output, or nothing if it's a public key output address. And then is just, we talked about that before, that is true if it's a just and false if it's a nothing. And if we filter by that, so the XS is now all the script inputs. And we check that the length of that list is exactly 2, because we expect 2, the oracle and the swap itself. So this is the first condition. we check that there are exactly these two script inputs. And now the second condition is that the seller actually gets paid. So this is the seller paid. How do we do that? So first, we compute the minimum price that has to be paid. So we check again with this find own input. Remember, that gives me the input that is just being validated. So it should be the swap input. If we don't find it, it's an error. If we do find it, we again compute the corresponding output, take the value, and use our helper function Lovelaces to check how many Lovelaces are there. So this is now, this Loveless in is how many Lovelaces are locked in this swapped UTXO. And then we use the price helper function that we defined before, given this amount of Lovelaces and the Oracle value that we looked up here, to compute the price. And then we can define this seller paid condition. So first we check how much he did pay. And there's a helper function in the Plutus libraries called value paid to, given info and a public key hash. It adds up all the values of all the outputs, the public key outputs that go to this address. So this is now the total value that is sent by this address to the seller. And now we use this as a class value of function to check the component of this value that is the O asset of the Oracle. Remember, that is the asset that the exchange rate of the Oracle is actually for. So in the US dollar example, this would give us now the US dollar tokens that are sent to the seller by this transaction. And we just check that there are at least as many as the mint price dictates. So we allow overpaying. So if the buyer wants to be generous, he can pay more tokens, but he must pay at least this minimum price that's determined by the exchange rate. So this is all. That's our swap validator. Then the usual boilerplate. So we define the swapping helper type that records the datum and redeemer. So again, datum is the pub key hash, the pub key of the seller. No interesting redeemer. Do the usual template Haskell stuff to compile this, given the Oracle to a script. And here we see earlier we had two arguments, the Oracle and the Oracle address. Now we don't need this. We just need the Oracle because, as I said before, we can compute the address from the Oracle using the Oracle address function. We just can't use that in Plutus code, in quoted code in this validator function itself. But here we, as expected, get away with just one parameter, the Oracle. Okay, so now we have the instance and we do the usual thing, get the validator, get the address. And now we can construct a couple of contracts. So the first one, offer swap, is for the seller if he wants to provide such a swap. And that takes as parameter the Oracle and an integer. That's the amount of Loveless he wants to offer. So we look up his own public key. And then as in the transaction, we want a transaction that locks this amount of Loveless in the swap contract. So we only need one constraint, must pay to the script. That takes the datum, which is our public key hash because we are the seller, and it takes the amount. So Loveless value of the amount we specified as an argument to this function. We submit and wait for confirmation and log a message that we offered so and so many Loveless for swap. Then a helper function that finds all swaps that satisfy a specific predicate. So given an Oracle and a predicate on pub key hashes, it gives us a list of all the UTXOs that that sit at this swap address. So again, the reference to the UTXO itself, and this public key hash is the datum of the UTXO. So that's as follows. So we use the UTXO add at the address. So that gives us all UTXOs sitting at this swap address. And then we use map maybe on the list that we get from this map. So this map maybe we can check. So if we import data.maybe and ask for map maybe. So this takes a function from A to maybe B and a list of A's and returns a list of B's. And the way it works is it applies this function to each A in this list. So we will get a bunch of maybe B's, so there can be just B's and nothings. And then it will throw away the nothings and just keep the justs and remove the just. So as an example, we could, for example, say f n int if we have an even integer, then we return just diff n2, so we divide it by 2, and if it's an odd integer, nothing. So that we okay, sorry, I must activate that extension. Okay, so now I can try that out. So if I try it on an even number, I get just half of it, and if I apply it to an odd number, I get nothing. And now I can use map maybe in combination with this f I just defined on a list of integers. So for example, I don't know, 2, 4, 10, 11, 13, 100. And I get now the list of the halves of the even numbers, but the odd ones are dropped. So I get 1 and 2, half of 2 and 4, and 10 is 5, 11 and 13 are dropped, and I get half of 100 is 50. So I want to use that to filter my UTXOs here in the find swap. So I use this function G. But first I define another helper function F that just takes one of the UTXOs I'm looking at and gives me a maybe pub key hash. And what I do is I first look up the datum hash. And again, this is in the maybe monad. So this do block is in the maybe monad. So I look up the datum hash attached to this output. That could fail. That's a maybe datum hash. But if it succeeds, so the hash, the datum hash is DH, then in the TX data field of the transaction, I look up this hash to get to the datum D, where D is of type data. And finally, I try to deserialize it basically from data to pub key hash. So I expect, of course, that at all these swap UTXOs, the datum will be there and it will be a public key hash. So in this case, I will get just that public key hash. Okay, and now this G function has now the right type. So it takes a pair of key and value from these UTXOs and returns a maybe key, value, and pub key hash. And what I do is, first I use my first helper function to get the public key hash, if it's there, so that's the datum now. Then I apply this, this predicate that was argument here to my helper function. And guard, we haven't seen that before, so in some monads, including maybe, this guard is available, and that takes something of type Boolean. And what it does is it fails if this Boolean is, if it's false, then this computation fails. And if it's true, it just continues. So that means I check whether this predicate, whether the datum of the UTXO satisfies my predicate. And if it does not, then this will return nothing. So I will drop this UTXO. And if it is, then I return this triple, consisting of the reference, the UTXO itself, and the datum encoded in it. And we will see how we use this find swaps in a bit, so this helper function. Right, the next contract I define is this retrieve swaps. So that's for the seller if he changes his mind and wants his swaps back. And so how does it work? It just takes the owner's public key hash. Now it uses our helper function, and here as predicate it checks that it's the swaps that belong to himself. So remember, the datum is the seller, the public key hash of the seller. So I check that I only take those UTXOs sitting at that swap address that belong to me. So this is now this XS. If there are none, then there's nothing to retrieve. So if it's the empty list, there's nothing to do. If it's not the empty list, I now construct a transaction that retrieves all of those. And how do I do that? So I take all the UTXOs in this list, and for each of them, I build a constraint and say I want to spend that UTXO. Must spend script output this UTXO. And as redeemer, just the unit. So now I have a list of constraints, and mconcat is a function that if I have a list of elements in the semigroup, it combines all of them. So, I mean, normally we did that explicitly. So we had, for example, two constraints, and we used this operator here to combine them together to one constraint. So now I have a list of constraints. I don't know how many elements there are, and with mconcat I can combine all of them together. So now I have this tx is now the constraint that all the UTXOs that belong to me that sit at the swap address, I want to consume in this one transaction. I want to get all the Lovelesses from all those swaps back. And as lookups for this to work, I must provide all the UTXOs, but that's, I mean, those I have. Those are in this list XS. So I don't care about this hash. I know it's mine anyway, this property key hash. So I have the oref and the O from all of these, and I can use map from list to turn this list of key value pairs into an actual map, and then apply this unspent outputs constraint to it to get me the lookup. So now when I try to solve this constraint and construct a transaction, I will find all these UTXOs I want to consume. And I must, as before, provide the validator of the oracle actually. No, sorry, not of the oracle, of the swap itself. It's parameterized by the oracle. Because I must I must include the validator script in the transaction because I want to consume those script outputs. Okay, and then I submit it, await until it's confirmed, and then I just say how many of these swaps I retrieved. Okay, and the interesting one is now this one, where I actually make use of the oracle. So this is, I want to use a swap. And I mean, there can be several swaps, and I didn't want to make it too complicated. So basically what I do is I look up my own funds. That's in this third module I mentioned earlier. That's why I have to import the funds module. We'll get to that in a second. But all that does this own funds module, this own funds contract, it checks my own wallet and adds up all the money I have. So funds is now of type value, contains all the funds I own. Because I want to check how much US dollar tokens or tokens I have to actually pay for these swaps. So given all my funds, I check how many of the tokens that we are talking about in the oracle I have. So that's now amount. I just log that as an information, how much I have. This find oracle function comes from the core module. We used it for some of the oracle functionality before. So it finds us the oracle, the UTXO that contains the oracle, and the value. If we don't find the oracle, then we just log a message that we didn't find it. And if we do find it, so oref and O reference the oracle UTXO, and X is the current exchange rate. So we log a message that we found it. We check our own public key. We now look for all available swaps where we are not the owner, so where the owner is not us. Now we use a helper function find. That's in the Haskell prelude. It's in data.list. So given a predicate on elements of a list, it finds us, maybe finds us one that satisfies this predicate. And this is defined here. And we give it two parameters. So the amount that we have, the assets that we own, and the current exchange rate. So this predicate now takes the amount we have, the current exchange rate, and now it goes over the elements of the swaps we found and returns whether this is a suitable swap or not. And all we do is we check that the price we would have to pay for that specific swap is at most as high as the tokens we own. And this get price function is defined above here. So given exchange rate and an output, we just use our price helper function and apply it to the Lovelesses contained in the swap and the exchange rate. So what this line does is it tries to find a swap that we can afford, where given the current exchange rate that the Oracle tells us and the amount locked in this swap UTXO, we have enough assets to actually pay for it. If we don't find such a swap, then we log a message that we didn't find such a swap. If we do find one, we just take the first one. I mean, that's not very realistic, of course, in a real world example. Would probably use, specify an exact amount, how much we want to swap or whatever. I just wanted to keep it simple because it doesn't matter. I mean, we're talking about oracles, not about swapping. It's just an example. So I just pick a swap that I can afford. And now I construct a transaction. So this is the output for the oracle. So that will be the existing value in the oracle. So the O, remember, is the oracle we found here. So this is the value that's already in the oracle, which will be the oracle NFT and maybe some fees that previous users of the oracle paid. And I just add my fee to that. So this is now the output value. Remember, when I use the oracle, I have to add fees. Okay, and the P is the price I have to pay actually. So I take the Lovelesses contained in the swap and the exchange rate from the oracle, use my price helper function, and this is just a number, an integer, how many of tokens I have to pay, and I convert that into a value with asset class value and this asset class. Right, now let's look at the constraints. The first constraint says we must use the oracle as an input. So this is the reference to the oracle, and as redeemer, we use the use redeemer. So this is now the first time we actually use the use redeemer. In the oracle code itself, we never used it. There we only used the update because the oracle provider is only responsible for providing the oracle values. The oracle provider doesn't care about using it. So now here in the swap contract, we actually want to use it. So that's the first constraint, consume the oracle input. Second constraint is consume the swap input. So there's a trivial redeemer, and this is the reference to the swap input. Third constraint is we want to pay to the oracle. So the value we computed before. So this is now this pay to other script, because now two scripts are in play, the oracle script and the swap script. So other script is now the oracle script. So we provide the oracle hash. As datum, we must use the existing datum. So we mustn't change the exchange rate when we use it. Only the operator of the oracle can change the exchange rate by using the update redeemer. And the value is the one we computed before, the V. So this was the existing value in the oracle and the fee that we have to pay. And last constraint is we must also pay the seller of the Loveless, and that's the price we calculated. And then we need these lookups to actually make that work. So we must provide the validator of the swap contract, we must provide the validator of the Oracle contract, and we must provide the two UTXOs we want to consume, the Oracle and the swap. And then the usual thing, so we submit it, we wait for confirmation, and we log a message that we actually made a swap, and just for information we log the price we paid. Okay, that's basically the raw contracts. Then I also provide like a bundle that contains all of them. So I define a schema for endpoints, offer to offer a swap of a given amount of ADA, retrieve to retrieve all my swaps, use to actually do a swap, and funds will just give me my currently available funds. Okay, and how do I define that? I use this select operator. I'm not sure whether we have talked about that before. So that is basically a contract that waits. I mean, if there are several endpoints, it waits until one of those is picked and then executes this one. So this will offer simultaneously the offer endpoint, the retrieve, the use, and the funds, and whatever of these components makes progress first will be executed. So and after I've done that, I just sequence with recursively calling myself again. So over and over again, I will offer these 4 endpoints. And these 4 endpoints are basically just wrappers of the contracts we defined before, except that now I actually add an endpoint. So for example, for offer, I now block with the offer endpoint until somebody from the outside provides me with an amount, an integer, and then I call the offer swap Oracle amount contract that I defined before. Same for retrieve, except there is no parameters, so I just block until somebody invokes the retrieve endpoint and then call my previously defined retrieve swaps contract. Same for use, and funds is a little bit different. Again, so this own funds comes from the module we haven't looked at yet, the funds module. But what this does is, ignore the H for a second, that's just an error handler, which I, by the way, use everywhere, so I must explain that anyway. So this blocks until this endpoint is invoked. Then I call the own funds function from the funds module, which gives me the V, the value that I own, and then I tell that. So I lock that value away. So when somebody calls the funds endpoint, I lock that to the state, and then it will be possible from the outside to look at that state. So that's a way to report back to the outside how much money I own. And now for the H, this is just an error handler. So it uses this handle error function that we saw before. And if there's an error, I just lock that error. So I wrap all these into this error handler. So if anything goes wrong in between, I don't want the whole thing to crash. I just lock the error and then continue. Okay, and that concludes the swap contract, the swap example.